The two-sample unpaired t-test is used to compare the means of two populations. Let's look at 3 step-by-step examples. But first, a quick review of the test. We want to know if two population means differ, but we can't measure both populations, so we take samples from each of them and calculate the sample means. The sample means estimate the population means, but sampling error makes them imprecise, so the question we ask is, what are the chances that the population means are the same based on how much the sample means differ from one another? If the sample means are almost equal, and there's lots of variation or noise, that's poor evidence that the population means are different. But if the sample means are very different, and there's little noise, that's good evidence that the population means are different. The t-test is how we take these two things into account. There are two basic kinds of t-tests, paired and unpaired. Paired tests look at cases such as before and after values for the same individuals, or twins where one of each pair is in each treatment. Each value has a single unique paired value in the other population. See our other video for more about the pairing process and examples of calculations for that kind of t-test. In this video, we're going to look at unpaired t-tests, ones in which the values don't have to be paired. In these, the individual data values don't directly correspond to one another, they come from two distinct populations, like taking values from two different times or locations, or studying the effects of two different treatments in two distinct populations. Let's look at how the unpaired t-test works. The way the unpaired t-test works is like this. We look at the samples collected from each population, and then calculate a new distribution based on the difference in the sample means, with a width based on the combined standard error of both datasets. In a situation like the one shown at the top and left, a big difference between the means of the samples and a little variation in the data will result in a large mean for the differences and a confidence interval that doesn't include 0. This suggests that the true difference between the populations is very unlikely to be 0, because the 0 is outside the confidence interval. The populations therefore seem to have different means. In a situation like the one shown at the bottom and right, a small difference between the means of the samples and more variation in the data will result in a small mean for the differences and a wider confidence interval that does include 0. This suggests that the true difference between the populations could easily be 0 because the 0 is inside the confidence interval. The populations therefore don't seem to have different means. Instead of actually creating these confidence intervals and doing this visual comparison, we calculate a t-value which represents the difference between the sample means relative to the width of the distribution. When the t-calculated value exceeds a critical value, that corresponds to situations when the confidence interval would not include the 0, but small t-calculated values tend to be when the confidence interval would include the 0. We actually have some choices to make when doing a two-sample t-test. The first choice is based on whether the variances of the populations are known. Keep in mind that this is the population variances, not the sample variances, which we can easily calculate from our data. Knowing the population variances is an unrealistic situation because how would we know the variances of the populations, but not know their means, and then just be able to look and see if they're different? No t-test required. Nevertheless, if this was the case, then technically we can do what is called a two-sample z-test. For this test, our z-calculated value comes from the equation shown, and the degrees of freedom is the sum of the sample sizes minus 2. We compare our calculated value to the z or normal distribution instead of the t-distribution to determine the significance of the test. In reality, you should never do this test unless you have huge sample sizes and feel very secure in your estimate of the population variances. This is somewhat unrealistic, so I personally don't recommend ever doing this test. Let's look at the two unpaired tests you should consider doing. If we don't know the population variances, but we're fairly sure that they're equal because we've done some other statistical test to compare them, we can do the unpaired homoscedastic t-test. For this test, the t-calculated value comes from the equation shown, which incorporates the sample means, the sample sizes, and a value called the pooled variance, the SP². The pooled variance is a weighted average of the sample variances, where the weighting is done based on the degrees of freedom for each sample. The overall degrees of freedom value for our test is the sum of the sample sizes minus 2. We compare the calculated t-value to the t-distribution for the matching degrees of freedom value to determine the significance of the test. If we don't know the population variances, and we don't want to assume that they're equal, either because we don't know or because we've tested and know that they aren't, we can do the unpaired heteroscedastic t-test. This is the most versatile t-test since it works with equal or unequal population variances and is also called the Welch's test. It's slightly less powerful than the homoscedastic test, but less likely to be performed under faulty assumptions since it doesn't rely on getting a comparison of the population variances right. For this test, the t-calculated value comes from the equation shown, which incorporates the sample means, the sample variances, and the sample sizes. Unfortunately, the degrees of freedom value for the heteroscedastic t-test is much more complicated than the ones we've seen before. The ugly equation shown there is used to calculate the overall degrees of freedom. It takes into account the two variances and the sample sizes and will return a non-integer value that we always round downwards. As before, we compare this calculated t-value to the t-distribution for the degrees of freedom to determine the significance of the test. Okay, so here's the formal procedure. First, we create a null hypothesis and alternative hypothesis. The null is that the means of the two populations are equal, and the alternative is that the means are not equal. Then, we get a t-calculated value using one of the equations from before, depending on whether we are assuming equality of the population variances or not. Then we compare that t-calculated value to various t-critical values taken from the t-distribution for the number of degrees of freedom for our sample. These correspond to different confidence intervals and probabilities. Then we determine the probability, the p-value, of seeing the t-calculated value as extreme as we do. What's the smallest alpha value we could pick, giving rise to the widest confidence interval, so that the difference between the sample means would be outside that interval? This p-value is effectively the probability of seeing our sample data if the null hypothesis is true. Finally, we decide to fail to reject our null hypothesis or reject our null hypothesis based on the p-value. If the p-value is not small, then we would fail to reject the null hypothesis and generally conclude that we lack evidence to decide that the population means are different. On the other hand, if the p-value is small, then we would decide to reject the null hypothesis, and thereby conclude that we have good evidence to decide that the population means are different. Okay, now let's look at 3 concrete examples. All 3 illustrate different important points. For our first example, let's think about the masses of fish caught at each of 2 different reefs to see if their sizes are different. Our data is the individual masses of a sample of fish from each population, and the questions we want to ask are the means of the fish at the 2 reefs equal, and with what confidence do we decide? When doing an unpaired t-test, the first step is to calculate the means and variances for each sample. If you need a reminder on how to calculate these, check out the Stats Examples video on calculating summary statistics. In this case, reef A gives us a mean of 31 with a variance of 3.200, and reef B gives us a mean of 29 with a variance of 4.444. These are the values we'll use for our unpaired t-test. First, let's look at how we would do a homoscedastic test. This is the one in which we assume the population variances are equal. We won't worry about how we determine equality of variances in this video, but Stats Examples has other videos on this topic available. First, we need the degrees of freedom, which is the sum of the sample sizes minus 2, which is 11 plus 10 minus 2 equals 19. Then we should calculate the pooled variance, since we'll be using it in our t-calculated equation. For this, we use the equations shown, the variances of 3.200 and 4.444, weighted by the degrees of freedom and divided by the overall degrees of freedom to give us a pooled variance of 3.78947. Then we plug the pooled variance into the equation shown, along with the sample means and sample sizes, to get a final t-calculated value of 2.3514. Now we take our values and compare them to values from the t-distribution. The first question will be how the magnitude, the absolute value, of the calculated t-value compares to the critical value that corresponds to an overall alpha value of 5%. We go to our t-table and look at the row for 19 degrees of freedom and the column for an alpha value of 0.025 since this is a two-tailed test. The value in the table is 2.093, which means that the middle 95% of this t-distribution runs from negative 2.093 to positive 2.903. Now our question is how the 2.3514 compares to this region. The 2.3514 is larger than the positive 2.093, which means that it is outside the center region. This means that our test will reject the null hypothesis of equal means for the 2 sides. We can therefore say that the mean masses are significantly different. We're not done, however. There are 2 more questions we have to answer. First, which population appears to have the larger mean? That's easy. We just compare the sample means, and that tells us which population mean appears larger. Of course, if our result wasn't significant, the sample means wouldn't tell us anything. But it is, so they do. Second, what is the p-value of our test? For this, we'll need to examine our t-table in more detail. To figure out the degree of significance for our test, we compare our calculated t-value to the whole set of critical values in our t-table. Remember that these values correspond to areas more extreme than a central region encompassing most of the t-distribution for 19 degrees of freedom as shown. The 2.3514 lies between 2 of the critical values in the table, the 2.205 and the 2.539. From our calculated t-value being more extreme than 2.205, we know that the p-value is less than 0.04. However, our calculated t-value is not more extreme than the 2.539, so we know that the p-value is not less than 0.02, it must be larger. We can therefore state that the mean mass of fish at reef A is significantly larger than the mean mass of fish at reef B, and then in parentheses 0.02 smaller than p smaller than 0.04. If we have access to a computer, it can provide the exact p-value of 0.0296, which we can see is less than 0.04, but more than 0.02. Now let's look at how we would do a heteroscedastic test, one in which we think the population variances aren't equal, or we just want to be cautious and not make the assumption of equality. First, we calculate the t-value, which is fairly straightforward. The difference in sample means go in the numerator, and the combined standard error is in the denominator. Plugging the values in gives us 2 divided by 0.85056, which is 2.3323 for our t-value. Then we need the degrees of freedom value, which is obtained using this huge and complicated equation, which uses the variances and sample sizes in several places. We just need to go slow and plug in everything carefully. When we do, we get 0.54074 divided by 0.03041, which is a value of 17.814. Degrees of freedom in tests are always integer values, so we round these calculated values. We always round downwards to simulate having less data and being conservative, rather than rounding upwards and acting as if we have more data than we do. The 17.814 gets rounded down to 17 degrees of freedom. Now that we have a t-calculated value and some degrees of freedom, the rest is just like the previous t-test. Now, how does the magnitude of this calculated t-value compare to the critical value that corresponds to an overall alpha value of 5%? We go to our t-table and look at the row for 17 degrees of freedom, and the column for an alpha value of 0.025, since this is a two-tailed test. The value in the table is 2.110. How does our 2.3323 compare to this? The 2.3323 is larger than the positive 2.110, which means it is outside the center region. This means that our test will reject the null hypothesis of equal means. We can therefore say that the mean masses are significantly different, and just like earlier, we know that the mean for reef A is larger than the mean for reef B, but we still have one more question. What is the p-value of our test? As before, for this we'll need to examine our t-table in more detail. We compare our calculated t-value to the whole set of critical values in our t-table for 17 degrees of freedom as shown. The 2.3323 lies between two of the critical values in the table, the 2.224 and the 2.567. From this, we know that the p-value is less than 0.04, but not less than 0.02. We can therefore state that the mean mass of fish at reef A is significantly larger than the mean mass of fish at reef B, p between 0.02 and 0.04. If we have access to a computer, it can provide the exact p-value of 0.0317, which we see is less than 0.04, but more than 0.02. We got the same result from the heteroscedastic test that we did for the homoscedastic test, with a couple of minor differences. Our t-calculated value was slightly larger for the homoscedastic test, and the threshold t-critical value was slightly smaller due to the higher degrees of freedom. This illustrates the slightly higher statistical power that the homoscedastic test has compared to the heteroscedastic test. Now let's consider a scenario in which doctors are testing a new medical procedure. The metric they're interested in is whether it will result in a shorter or longer recovery time, so they perform the old procedure on 8 patients as a control and the new procedure on 8 patients. This isn't a paired test, even though the sample sizes are the same, because there's nothing that connects specific patients across the two treatments, so we have to use an unpaired technique. We then ask if the mean recovery times for these two procedures are equal, and with what confidence do we decide. The first step is to calculate the sample means and variances for our equations. The mean for the old procedure is 16, with a variance of 5.1429, and the mean for the new procedure is 14, with a variance of 6.8571. Based on these, it looks like the new procedure may have a shorter recovery time, but we don't know if this is genuine unless the difference is statistically significant. This is our data. The degrees of freedom is the sum of the sample sizes minus 2, which is 8 plus 8 minus 2 equals 14. Next, the pooled variance using the equation shown. The variances of 5.1429 and 6.8571, weighted by the degrees of freedom and divided by the overall degrees of freedom, gives us a pooled variance of 6.000. Then we plug the pooled variance into the equation shown, along with the sample means and sample sizes, to get a final t-calculated value of 1.6330. Comparing our t-calculated value to the critical values for 14 degrees of freedom, we can see that 1.6330 is not as extreme as the critical value for an overall alpha of 0.05, which is 2.145. We won't be able to reject the null hypothesis of equal means because p is larger than 0.05. Therefore, the mean recovery times for the old and new procedure are not significantly different. To get a better sense of what the non-significant p-value is, we look at the rest of the t-values on the row, and we see that the t-calculated value of 1.6330 lies between the values of 1.345 and 1.761, which correspond to overall p-values of 0.2 and 0.1. We therefore state that the mean recovery times in the two treatment groups are not significantly different, in parentheses 0.1 smaller than p smaller than 0.2. With a computer, we can obtain the exact p-value, which is 0.1248. The data doesn't prove that the new procedure doesn't alter the recovery times, but it demonstrates a lack of evidence that it does. If we do a heteroscedastic t-test instead, we start with the same data shown here. First, we use the heteroscedastic t-test equation. Plugging in the means and variances gives us 2 divided by 0.85056 to get a t-calculated value of 1.6330. It's not a coincidence that our t-calculated value is the same as the one we got for the homoscedastic test. This will always happen if the sample sizes are equal. Next, the degrees of freedom using the complicated equation. Plugging in values carefully gives us a value of 13.72 for the degrees of freedom, which we round down to 13. Comparing our t-calculated value to the critical values for 13 degrees of freedom, we can see that the 1.6330 is not as extreme as the critical value for an overall alpha of 0.05, which is now 2.160 because our degrees of freedom decreased from 14 to 13. As before, we won't be able to reject the null hypothesis of equal means because p is larger than 0.05, and the mean recovery times for the old and new procedure are not significantly different. Looking at the rest of the t-values on the row, we can see that the t-calculated value of 1.6330 lies between the values of 1.350 and 1.771, which correspond to overall p-values of 0.2 and 0.1. We therefore state that the mean recovery times in the two treatments are not significantly different, 0.1 less than p less than 0.2. With a computer, we can obtain the precise p-value, which is 0.1252. The slightly higher p-value reflects the lower degrees of freedom value because this is a heteroscedastic test instead of a homoscedastic test. Now let's consider a scenario in which we've measured the number of cracks in structures in two different locations. Perhaps we're interested in whether the different locations alter the long-term integrity of the buildings. Our questions will be, are the mean number of cracks the same, and with what degree of confidence do we decide? The first step is to calculate the sample means and variances for our two sites. The means for the sites are 11 and 6, and the variances are 23.6 and 14. Based on these, it looks like site 1 has more cracks, but we don't know if this is genuine unless the difference is statistically significant. Here's our data again. The degrees of freedom is the sum of the sample sizes minus 2, which is 6 plus 8 minus 2 equals 12. We calculate the pooled variance using the equation shown and the variances of 23.6 and 14 to get a pooled variance of 18.000. Then we plug the pooled variance into the equation shown along with the sample means and sample sizes to get a final t-calculated value of 2.1822. Comparing our t-calculated value to the critical values for 14 degrees of freedom, we can see that the 2.1822 is slightly more extreme than 2.179, which is the critical value for an overall alpha value of 0.05. We can therefore reject the null hypothesis of equal means because p is smaller than 0.05, and the mean number of cracks at site 1 is significantly larger than the mean number of cracks at site 2. To narrow down the p-value, we look at the rest of the t-values on the row, and we see that the t-calculated value of 2.1822 lies between the values of 2.179 and 2.303, which correspond to overall p-values of 0.05 and 0.04. We therefore state that the mean number of cracks at site 1 is significantly larger than the mean number of cracks at site 2, p between 0.04 and 0.05. With a computer, we can obtain the precise p-value, which is 0.0497. A p-value only barely less than 0.05 isn't super convincing, but our result is a significant difference between these two sites. Now if we do a heteroscedastic t-test, we would start with the same data as before. First, we use the heteroscedastic t-test equation. Plugging in the means and variances gives us a t-calculated value of 2.0973, slightly less than the one from the homoscedastic t-test. Next, the degrees of freedom using the complicated equation. Plugging in values carefully gives us a value of 9.1458 for the degrees of freedom, which we round down to 9. Note that this is considerably lower than the 12 we had in the homoscedastic case. Comparing our t-calculated value to the critical values for 9 degrees of freedom, we can see that 2.0973 is not as extreme as the critical value for an overall alpha of 0.05, which is now 2.262 because our degrees of freedom decreased from 12 to 9. Unlike before, we now aren't able to reject the null hypothesis of equal means because p is larger than 0.05, and we therefore conclude that the mean number of cracks at site 1 is not significantly different from the mean number of cracks at site 2. Looking at the rest of the t-values on the row, we see that the t-calculated value of 2.0973 lies between the values of 1.833 and 2.262, which correspond to overall p-values of 0.1 and 0.05. We would therefore state that the mean number of cracks at site 1 is not significantly different from the mean number of cracks at site 2, p between 0.05 and 0.1. With a computer, we can obtain the precise p-value, which is 0.0649. This pair of tests shows that the result we get can depend on the test we use. The exact same data analyzed with a homoscedastic test gave a significant difference, whereas an analysis using the heteroscedastic test gave a non-significant difference. Our conclusion comes down to our assumption about the population variances, and a type 2 error in that test could lead us to perform the homoscedastic test and get a significant result, when we should have done a heteroscedastic test and not rejected the null hypothesis. This shows the double-edged sword of the homoscedastic test. It has more power, but is prone to an extra risk of type 2 error compared to the heteroscedastic test, which doesn't carry the extra risk from the variance equality assumption. This is also one of the reasons why we should not overinterpret borderline p-values. In reality, if we get a test with a p-value this close to 0.05, we should probably redo the entire experiment with a larger sample size and see what happens when we have better data. Let's go over a few things to remember. First, when the sample sizes are equal, the t-calculated value will be the same for both the homoscedastic and the heteroscedastic procedure. The homoscedastic t-test has slightly more power for two reasons. First, the t-calculated value will be equal or larger than the heteroscedastic, making it more likely to exceed the critical value for an alpha of 0.05. Second, the degrees of freedom will be larger, which means the critical values will be smaller, also making it more likely to exceed the critical value for an alpha of 0.05. Even though the homoscedastic test seems better because it has more power, the homoscedastic t-test does carry an extra risk of type 2 error when we decide that the population variances are equal. For this reason, my advice is that we should generally stick to the heteroscedastic t-test in the real world. The two tests will only differ in their conclusions if p is close to 0.05, when we should be extra cautious anyway. I hope you found these examples useful. The Stats Examples website has a high-resolution PDF of this final screen and a bunch of other completely free statistics resources. Please help others to find this video if they're having trouble doing the t-test by liking, subscribing, or commenting.